So this week we're covering compound interest and present value. So the past couple of weeks we did simple interest calculations, and then we did simple discounting calculations. This is where we're kind of combining that and adding a layer to it. So when you get a loan, typically the loan has some compounding related to it. Or if you get interest in a bank account, it's usually got some compounding to it. So when I got my first car loan, it was simple interest, where the calculations that we had been doing, it was it's not compounded daily. It was simple interest, but the period was in days, but used as months. And so you could calculate the interest that you would pay by the end of the term of the loan pretty easily with the simple IPERT equation or IPERT equation that we've been using all along. However, whether you have stocks or you have interest-bearing accounts on your savings account, or maybe it's a mutual fund, most of that debt and most of that generated interest is going to be compounded over a certain period of time. It could be compounded every month. It could be compounded every day. It could be compounded every week. It could be compounded every year or every half a year, every quarter. And so the rate at which the compounding occurs is going to change the actual effective rate of the interest that you're generating. So if you get 2% annual interest, but it's compounded every single day, your actual effective rate is going to be higher than 2% because it's taking 2% of what you have on day 2 instead of what you had on day 1. So for example, like if you put a penny in your account on day 1, but you started with $1, the interest on day 2 is going to be based on that dollar and a penny, not based on the original dollar. Whereas if it's compounded every week, it's going to be whatever the principal balance is at the beginning of the week. And if it's compounded every month, it's based on the principal amount at the beginning of the month. And if it's semi-annually, it's every 6 months. So the shorter that time period is, the more likely you are to generate additional value. Additionally, you could even have continuous compounding where you would use like an exponential function, but we're not going to get to that in this course. So the roadmap and objectives for today, we're going to focus on calculating compound interest, which is also known as future value. We're going to compare kind of what we calculate with simple interest with compound interest. We're going to calculate the effective rate. So like I said, just because you're getting 2%, if it's compounded daily, it's going to be higher than that. And we can do this manually, or we can do by table lookup. The textbook is actually a little too simple, I think. So I'm adding in the formula to be able to calculate this without the table into your slideshow. And it's your choice as to whether or not you want to use the table or the equation. If I don't give you a problem on the quiz or on the exam that is within the table, then you'd have to use the formula, but I'm going to try and make problems where you could use either one. And then present value is basically kind of like a backwards looking measurement, where we had the simple discounting notes where you paid all your interest up front. So that way, you didn't really pay in a way you pay your interest up front, but basically you pay, the maturity value is what you borrowed versus what you borrowed plus the interest. And so the effective rate was higher. So what we'll do now is when you're using present value, and let's say you want $1 million in 20 years. Well, the question is, how much money do you need to set aside today so that that money that you set aside today will be worth $1 million in 20 years? Chances are you probably don't have enough in your account right now, but maybe you do. depending on the right type of investment. So basically, we're going to be looking at using present value, determining, okay, how much is the money that is going to be worth this much in X number of years worth today? And if you're doing depreciation calculations and stuff like that, which we'll do in chapter 17, you might actually use present value in the opposite direction, where you're discounting money that's valuable today and how much less it'll be worth in the future. So when we're talking about compounding, it basically means that we're calculating the interest periodically instead of once or once a year. So basically with your simple interest loan, you were essentially you were still compounding, but you were only doing it once a year because the stated interest rate is considered an APY, annual percent per year. And so, or average percent per year, depends on who you ask. The compounding is just annually. So instead of it being updating it every day or every week, you're updating it once a year, so it doesn't seem like it's compounding. And then compound interest is the interest on the principal plus the interest of the prior periods. So that's why when you're paying back like student loan debt, or you have stocks, or if you have like a savings account with interest on it, it kind of grows in a way, it feels like exponentially because it is growing exponentially. Basically, so if you have a 2% loan, or if you're getting 2% in your savings account, but it's compounded every day, then that 2% is going to be compounded on top of the 2% on top of the 2% over time. So you actually end up getting more in terms of your interest than what is actually stated nominally. So future value is basically kind of like your maturity value, but it's basically saying how much money are you going to owe, or how much money do you have at the end of the last period. And then present value saying what is the value of something today. So if you want to know how much $20,000 is going to be worth, or how much $20,000 in 10 years is worth today, you can calculate a present value that kind of looks backwards and says, okay, well, based on interest rates or inflation rates, that $14,207 is worth $20,000 10 years from now. And so compounding is more realistic to what you're going to see out in the banking sector and out in your out in the world. And so we're going to learn about that tonight. I'm trying to make sure that I can hear. Because I think someone's on mute. I want to make sure that if you're asking a question, that I can hear you. So. Hopefully I'll be able to hear. Okay, so I had my microphone switch for a second. Does anybody have any questions out there? Okay. So when we talk about compounding, again, if you compound annually, it's just once a year. So basically, if you opened a loan on November 2nd, so yesterday, it would be compounded next November 2nd. If you compound semi-annually, that's every 6 months, which would mean that, what's 6 months from October? April. So April 2nd, you would get compounding. If you compound quarterly, that would be every 3 months. So that would mean that in January, you would compound the interest. If it's monthly, then that would mean on December 2nd, you would compound the interest. And then if you do compounding daily, that means today was the first time it was compounded, and it would be compounded again tomorrow, and the next day, and the next day, and the next day, and the next day. So your effective rate could grow, or your effective rate is higher than your actual nominal rate because it's updating. So if you have a lot of money or a lot of debt, it can grow substantially, which is why typically people that already have a lot of financial capital maintain it, because they can get these kind of compounded values on a daily basis. So this is how compounding works. This is an example of 8% compounding over 4 periods. And so this is more saying over 4 years. So each period is 1 year, because we're using an 8% rate. If it was 8% over and we were doing quarterly, then we would actually have 16 periods, and each period you would get a 2% rate because you're dividing it by each quarter. So again, this is a very simple issue of, or example of compounding, where basically you have an 8% interest rate, and then you have to, and then it's growing over 4 years. So in this case, we're not thinking about debt. We're probably thinking about like a savings account or something like that. So if you're getting 8%, sign me up for that. So what you'll do is after the first period, that dollar is going to be worth $1.08 because you're taking 8% of the principal amount, which is $1, and then you're getting the interest on it. So that would be $1.08. And then if you go to the second year, you're not compounding off that $1 anymore. You're compounding off that 8 cents plus the dollar. So you're going to take 8% of the $1.08, and that's about 8.64 cents. So you add that to the $1.08, and then you're at about $1.16.64. And then in the third year, you're going to take 8% of what you had initially, and that's going to give you about $1.2597 when you add it together, meaning that your interest wasn't 8 cents because you're taking off the $1.16. So it's probably somewhere around 9.3 cents. And then you compound again a year later, and then it's 8% of the $1.26. And so you get 10 cents of interest instead of just 8 cents every single year because your initial value was $1. So whenever you compound, you're basically taking a percentage of what the total value is at that moment, not based on the initial principal. Because whenever you compound, whatever interest was accrued prior to that compounding moment is now considered part of the principal. So if you have $1 and you get a 5% rate, you would get 5 cents. But when you compound again, that 5 cents is not considered interest now, it's considered part of the principal. So you'd be taking 5% of the $1.05, and then you take 5% of the $1.05 plus 5% of the $1.05, then 5% of the $1.05, blah, 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 blah. And it just keeps growing and growing over time, which is why chances are if you're getting 2% interest, it's not going to take you 50 years to double the amount of principal that you have, because every year that 2% is being taken of 1.02% of whatever it previously was, or 1.02 times it was previously. So the effective rate is actually going to be larger than the actual listed interest rate because of compounding. So here, if you want to do this manually, again, if you take 8% of $1, it's 8 cents. If you add it to the beginning balance, you get $1.08. And then what you're doing is, again, that interest turns into principal. So then you take 8% of $1.08, that becomes about 9 cents. You add that to that, then it's about $1.17. And then again, that interest from the second year becomes part of the principal for the third year. So you take 8% of $1.17, that becomes about 9 cents. Add that to the $1.17, you're at $1.26. and then the interest from year 3 becomes part of the principal of year 4. So you take 8% of $1.26, that's about 10 cents, add that to the $1.26, and then you're at about $1.36. So if you were to ignore compounding, you would reasonably expect that the principal or the total value would be $1.32 because you'd be getting 8 cents a year off of the initial principal. But the reality is you're getting 8% off of the new updated principal every time you compound. And so your effective rate is actually going to be higher than 8%. And the more times it gets compounded, the higher that effective rate. So if you only compound it once a year, it's going to be slightly higher than 8%. If you compound it twice a year, it's going to be larger. You compound it 4 times a year, it's going to be larger. Every single day, it's going to be even larger than that. So if you end up compounding more frequently than once a year, then you're going to have to think about, one, how many times you're compounding it, which is going to be the number of periods. And then you also need to take into account what the rate is for each period that you're taking it for. Because the listed rate of 8% is not every, you don't take 8% every time you compound it. You take 8%, you take the relativeness of that 8% when you compound it. So like if you're compounding 4 times a year, you're not compounding it based on 8% because only 3 months have passed. So if 3 months out of 12 months is 1/4, and you're getting 8% for the entire year, it's going to compound at the rate of 2% each quarter. So really, you're getting 2% interest every quarter. But the amount updates every time it compounds, so your effective rate is still going to be higher than the 8% at the end of the year. So if we're compounding $100 for 4 years at 8%, then that means that annually there would be 4 periods, and the effective rate for each period would be 8% divided by 1, which is 8%. If you do it twice a year, then that means there's going to be 8 periods because you're multiplying the number of years times the number of periods. So you get 8, and then each period is going to be worth half of 8% because you want to credit the existing principal that's there more frequently, but you have to also divvy up the total slice of the interest over the course of the year into reasonable portions relative to how frequently you're doing it. So if you're doing it twice a year, it should be 4% twice a year. If you're doing it annually, it's 8% once a year. If you're doing it at 10% daily, then it's whatever 10 over 360 or 10 over 365 is, 360 or 365 times a year. If you're doing it quarterly, well, then you have 16 periods, 4 years times 4 quarters. And so each of those is going to be 2%. So when you're doing this, your effective rate is still going to be higher, but it's not going to be crazy, because if you compounded 8% every single time, it would actually be, you'd be multiplying it by a larger amount. So like if you compounded the full 8% quarterly, then you'd actually have a interest rate of 32%, not 8%, which would be great, but not realistic. So annually, N is going to be 4 and R is going to be 8. If it's semi-annually, N would be 8 and R would be 4. If it's quarterly, then N is 16 and R is 2. If you did it monthly, then N would be 48 and R would be 0.67. Because if you did it monthly, it would be 4 times 12, which is 48. And then it would be 8 over 12, which is 0.67%. So any questions so far? Okay. So how do we compare this to our simple interest that we calculated a couple of chapters ago? So if Bill Smith deposits $80 in a savings account for 4 years and the annual interest rate is 8%, what is the calculation? So we're going to say this is compounded annually. And then here we have simple interest. So the IPERT equation would say the total dollar value of the interest is going to be the initial $80, which is P, principal, times the rate, which is annual, which is 8%, times the number of years, which is 4. When you do 80 times 0.08 times 4, you get $25 of money that Bill would have 4 years from now is $105.60. Now, if it's compounded annually, I'm going to turn my video off because it says my internet connection is shaky right now. Hopefully that'll help. I've been having some internet connectivity issues the past couple days here. So so if you're compounding this annually, then the difference is that every year we're going to update the principal balance. And so the interest is going to be based on the principal that exists at the beginning of that year instead of the principal that you started with 4 years ago. That's what simple interest does. It's taking the interest based on what your initial value was day one. Here it's saying, what's the initial value day one of the period in which we're analyzing. So in year one, 8% of Bill's going to get 8% of $80, which is $6.40, which means that their principal value when they get compounded the second time is going to be $86.40. So 8% of $86.40 is $6.91. Add that to the existing $86.40, you end up with $93.31. So $93.31 becomes the year 3 principal balance. Then your new principal value for the last time it's compounded is 177. Multiply that times 8%, you get $8.06. Add that to 177, and you get a final value of 108.83, which is clearly higher than what we had with simple interest. If we want the actual dollar amount of the interest, just compare the final value from the initial value, and it turns out that we generated $28.83 in interest. So this generated more interest than the simple interest investment did, because that compounding is basing it off of a higher value every year instead of the initial value from the beginning. So we can also use a table to look this up. So the first step, if I gave you an example, would be to find the number of periods. So let's see. For compounding, banks typically use daily. And they use compounding daily. So banks for car loans will often use simple interest. But typically your banks for interest itself, actually that's not true. Well, when it comes to debt, things are typically compounded daily. But if you're actually getting like an interest-bearing account at a bank, typically they compound monthly. So It really just depends. Banks typically for interest-bearing accounts will compound monthly. I actually have been getting involved with involved, like it sounds like it's like a bad thing, or I'm actually doing something active. But bank, not banks, I'm getting involved more with cryptocurrency. Not because I'm a huge believer in it, but there is some different types of cryptocurrencies that are doing some different things with interest. So a lot of them are, so there's a stable coin where it's basically I buy a dollar, I spend a dollar, I get a dollar's worth of this stable coin. So it's tied exactly to the dollar. So if the dollar is a dollar, then it's worth a dollar. If it's 99 cents, it's worth 99 cents in real dollars. The exchange that I'm using is offering 1% interest on it, and it's compounded daily. I have another cryptocurrency that has what's known as staking, where basically its effective rate is, or its interest rate is about 4.6%, but that is compounded every 3 days. And then I have another one that's compounded every week. So in the cryptocurrency space, you can get a bunch of different, and then I also have an interest-bearing account that compounds monthly. So most banks do monthly when it comes to interest-bearing accounts, but when it comes to debt repayment, it's usually a daily compounding, just to mess with you. A good question. So going back to if you want to use the table method to find an effective rate, what it does is it saves the time of having to plug in a bunch of calculations. I mean, the formula is not that hard, but if you're worried about typing into your phone or type into a calculator correctly, and you have numbers that fit with the table's pretty easy. But the legwork is in determining, okay, what is the rate and what is the number of periods? So, for example, if the annual rate of interest is, let's say, 8%, and it is compounded quarterly, then the number of periods and the length of time is 3 years. Then the number of periods is going to be 3 years times 4 quarters, which is 12. So the rate is going to be the 8% divided by the number of times it's compounded. So if it's quarterly, it's 4 times. So you would get 8 divided by 4, which is 2%. So then what you would do is you would go to the period column and you would find where it's 12. And then you would go across the row to find the rate, which is 2%. And then basically you'll get some sort of multiplier. And what you'll do is you'll take that initial multiplier, multiply it times the original, and then that'll give you the compounded value at the end of the period. So let's say this was $500. What we would do is we would find the table and it would say, okay, 12 periods, 2%, this is the number. So if we have 12 periods at 2%, we would get, so we look here, it's 12 periods, 2%, we get a rate, a multiplier of 1.2682. So if we go back here, we would do, what was it, 1.2682 times the $500, and that would tell us the final answer, which is going to be some number. 1.2682 times 500 is $634.10. And if we subtract 500 from that, it turns out that the amount of interest we received was $134.10. So that means that because it was compounded quarterly at 8% for 3 years, to find the number of periods. If it's compounded annually, it's just the number of years. But if it's compounded anything other than that, you got to multiply it times the number of years. And then the effective, and not the effective rate, but the actual rate is not the full 8%. It's some proportion of it dependent upon the number of times you're compounding it. Since we're compounding it 4 times a year, it's 8/4, which is 2, which is why we found the 2 column here, and we compared it to the number of periods, which is 3 times 4, so 12 here. And then where they match up is this right here, and that's the multiplier. That's not that you don't do that 3 times, you don't do it 5 times. That's the multiplier times the principal amount that'll give you the correct answer. So we could confirm this. We could actually multiply $500 times 0.02, and then do that again, then do that again, and do that 10 more times after that. And what you should get is the same answer. You should get that $634.10 as your final future value of that. Pam Donahue is depositing $8,000 into her savings account that pays 6% interest quarterly, or compounded quarterly. So what will be the balance of her account at the end of 5 years? So the number of years is 5. It's being compounded quarterly, so we need to multiply. So you get 1.5% as your rate. And then the table factor was found through the table that is here, but we don't actually have 20 on this table. And so 1.5, we'd have to go out to 20, which we don't have on this table. But you would end up getting a factor of 1.3469. So if you multiply the 1.3469 times 8,000, you get a compounded amount, aka your future value, which is 10,775.20. And so if you want to determine how much interest you earned, you subtract 8,000 from that, and you get 2775.20. And that would be the interest that you acquired or incurred. So as I said before, or I've mentioned it probably about 5 times already, the effective rate is the actual interest rate that you're getting. And it's basically the ratio of how much interest you received over the principal amount that you started with, which is the same thing that we did last week, where when you did discounting, your effective rate was actually higher than the actual amount of interest that was stated on the loan. The interest rate that is stated on the loan is called your nominal rate. So if you're paying 8%, that's what's stated. And the way the calculation is done is based on that 8%. But the actual effective rate is going to be the interest that you accrue divided by the principal amount that you started with at the beginning of that year. And so that's why when we did the simple discounting last week, you ended up with a effective rate in terms of how much interest you were actually paying back that was higher because the actual amount that you received was less than the stated value. So you take out a loan for $14,000 with simple interest, you're paying back the 14 that you get the 14,000, you're paying $800 or whatever, and then the interest that you pay back is going to be divided by the 13,800 whatever, not the full 14,000. And so as a result, you end up with an effective rate that is higher than what is stated on the loan. So if we go back to this example, we can compare. Trying to find one that was after 1 year. So if we go back to this example that I did, we can determine the effective rate by just taking point. Well, we'd have to do it 4 times, so it would be annoying, but I'll do it anyways. So you get $10 the first time you compound. And then you get $10.20 the second time you compound. And then you get $10.40 the third time you compound. And then the fourth time you compound, you get $10.61. And so your total amount at the end of year 1 is $540. At what was the interest rate? 8%. Whoops, I did, yeah, 8%. So you do 2% every time you. And you get an effective rate of 8.24%. So that's how you calculate it. You take the interest that you generate over a year, divide it by the principal that you started with at the beginning of the year, and then that gives you your effective rate. So in this case, even though the actual rate is 8%, the effective rate is 8.24% due to this compounding factor. So here's another example. If we compound quarterly versus semi-annually, so the interest rate is the same. The nominal interest rate is 8% in both examples. The difference is that Sun Bank is going to compound it twice and Blue Bank is going to compound it once. So in this case, each time they compound, it's 4%. And then each time they compound here, it's 2%. But the frequency of the compounding is actually going to yield a higher effective rate, because even though you're getting 4% every time you compound in Sun Bank side on the right side, it's only happening twice. Meanwhile, that 2% is happening 4 times. So the amount is going to be larger every time you compound. So if you compound 3 times, the principal amount is going to be larger every time you compound, which is going to make that effective rate even higher. So if we start with $8,000 and we do the table lookup method, so if we go to this table, we have a rate of 2% when we compound quarterly, and we're doing it over 1 year, so we only have 4 periods. So your multiplier is going to be 1.0824, which is what we have here. And then for Sun Bank, the rate is going to be 4%, but the period is only going to be 2. And so your multiplier is 1.0816. So you multiply times 1.0816. They were both $8,000. So you multiply both by 8,000, and then you get 8,659.20 as your final value after the year versus 8,652.80. Subtract the initial amount. That gives you the amount of interest. This gives you the amount of interest. And so if you want to find the effective rate, you take the initial value or you be taking the interest over the initial value, and you get 0.0824, which is 8.24%, versus 0.0816, which is 8.16%. Since this was only 1 year's worth of compounding, you could actually get a giveaway because the multiplier told you what the effective rate was going to be. It's 8.24% for Blue Bank and 8.16% for Sun Bank. So the more times you compound with the same interest rate annually and the same principal amount, your effective rate is going to be higher, even though you're adding less interest each time, but you're doing it more often, which benefits growth. So any questions about this? So this little graph right here shows you that the effective rate increases the more frequently you compound. So if you have the same annual interest rate, the same nominal interest rate, same beginning balance, if you only compound once, you get the full 6%, but nothing more. If you compound twice, it goes up to 6.09. If you compound every quarter, so once every 3 months, it goes up to 6.14%. And then if you compound every day, then it jumps up to 6.18%. So the more you compound, the higher the effective interest rate, even though the nominal interest rate remains the same and the beginning balance is the same. What if you want to compound daily? Well, this is using the ordinary interest method where there's a 360-day compounding versus the 365-day compounding. I don't know which days they don't compound. If you do a 360-day basis, maybe Christmas and New Year's and other federal holidays, I'm not quite sure. But essentially, this is going to, this table is a little different because the period on the left-hand side is years, not days. So, because if you were going to have a table with daily compounding, you would it would be humongous, because if you have 2 years worth of data, that's 720 periods. So what this table does, as opposed to the previous table where you were dividing, you had to divide the annual rate by the number of compoundings to get the number of periods, or multiplied for the number of periods, divide to get the rate. This table is automatically assuming that you are going to, this table is automatically assuming that you're going for the whole year. So this period column is years, and then these are the annual rates. Although I wish that I got a 10% annual rate in any regard for anything, because most of the time it's probably something like 0% or 1% or 2%. So for this table again, if you want to calculate what $900 compounded daily for 25 years will grow to if it's growing at 6%, you go to this 6% as the annual percentage, 25 years. This multiplier is there, and that tells you how much to multiply that initial value by. So we're actually going to multiply the initial value by 4.4811, and then multiply that times 900, and you end up with $4,032.99. I don't know why this is saying 6%. And I don't know why this is saying 5. They always put these little typos in to mess with me. But if you wanted to do an example with 5 and 7%, so these aren't going here. So get rid of those arrows. This factor goes with this problem here. But if you want to do 5 years, 7% rate, then you could go to the table. Here's 7%. Here's 5 years. And you would get 1.4190. So 1.4190 times 5 would give you 1.419 times the initial value, $900, would give you $1277.10 for this very specific example here of 5 years and a 7% rate. So that's how you calculate those things. But, and then I'll get to present value in a second. I guess I'm going to jump ahead because I thought this slide was earlier. If you want to ignore the table altogether and calculate these, the total amount, you can use this formula. So that table value is in this box right here. The principal value is the initial value that you start with. That multiplier value that you're generating or getting from the table is calculated by using this formula. So if you have an 8% interest rate, then you would put 0.08 for the interest rate here for R. N is how many times it's going to be compounded. So if we're doing quarterly, then this would be 4. And then the exponential factor is the same 4 value times the number of years. So if we do 3 years, then that means that this would be multiplied by 3. So if we wanted to calculate this, we would do 1 plus 0.08 over 4, which is really 0.02, to the power of 4 times 3. So we would get 12. So if we do 1.02 to the 12th power, we get a calculation of 1.2682. Now, what we can do is we can compare this to the table we just looked at. And so if we do 8% quarterly for 3 years, that means the number of periods is going to be 12. And the rate is going to be 2%. So if we go to the table and we find 2% for the rate and 12 for the periods, we should get this number. So let's go back and look. So if we have 12 periods, 2%, we get 1.2682. If we go back here, we get 1.2682. So if you do not have the table, you can calculate the multiplier that goes to this principal amount just with this formula. You just have to remember what each thing represents. So again, your rate is going to be the annual rate divided by the times you're compounding, but remember it's a decimal, not a percentage. So you'd go from 8 to 0.08. And then the squaring and the exponent doing the same calculation over and over and over again to the number of times to the number of periods per year times the number of years. So rather than have to do this over and over and over again, you can just you can determine the number of times you're going to do it and then calculate it as an exponent. And then that gives you the same number that you got in that original table. So on the homework, I may give you a table-free, an untable solvable problem. So that way you can learn how to use this formula, because most students learn using this formula. So, does anybody have any questions about how I just calculated this or how it matches up with what we did in the table? Okay. So the last thing we have to talk about is present value. So present value is basically trying to figure out what is the current value of something that is worth a certain value in the future. So what this graph is telling us is we're kind of working backwards. We want to know how much $1 4 years from now is worth today. So essentially, we're doing the same calculation that we were doing with future value, but backwards. So essentially, this is like the chapter 11 version of the compounding. So the chapter 10 version of the compounding was the future value calculations that we just did. The discounting part, the chapter 11 version of the compounding, is this, where we're starting, or we know how much, we're trying to figure out how much we need to save over time. Okay, so you got a target in terms of how much money you need in the future, and you have an interest-bearing account, or you're putting it in mutual funds or treasury bills or something like that, where you know that you're going to get 8% a year, which is great. If you could guarantee 8%, that'd be awesome. If you could do that and you have a target amount, then you can determine, okay, well, this is how much I want in 5 years. So how much do I have to put in now so that I can just set it and forget it, in 5 years from now, magically, poof, I'll have the money that I wanted. So in this case, this graph is telling us, okay, 4 periods from now or 4 years from now, we want to know what $1 is going to be worth. We want to know what in today's dollars, how much $1 4 years from now is worth right now. So this table is saying that $1 4 years from now is going to be worth 93 cents, and 3 years from now is going to be 86 cents. 2 years from now is going to be 80 cents a year from now, and currently is $73.50. So if our inflation rate was 8%, it would say that $1 today is worth $73.50 4 years from now. But if you're looking at it from the perspective of growth, it's saying that if you invested $73.50 today, you'd have $1 4 years from now, based on that 8% return on your investment. So again, we're going to have a table lookup ability, and then we have a formula where we can find a similar value. So the first step is to find the number of periods. So how many times is the interest going to be compounded in a year? So if it's compounded quarterly, you would do the same thing where you'd multiply it by 4. So if you have 3 years quarterly, then the number of periods, like always, would be 4 times 3, which is 12. Find the rate. So if your rate is, say, I don't know, 5%, you would divide 5 over 4, which is 1.25%. And that would be the amount that it is compounded every time you hit a new quarter. So it'll be compounded at 1.25%. So then on the table, you're going to do the period column thing again, where you're like, oh, well, you have 12 periods. So we're going to look at that. And then we're going to look at the row for the rate. And then we're going to find it's 1.25% and find that matching number. and then you'll multiply that factor by the future value, and that'll give you the present value. So before we were getting some greater than 1 multipliers, these multipliers are going to be less than 1 because we're actually shrinking the value. We're saying, okay, in the future, it's going to be worth the nominal value that we see today. But how much in today's dollars is that dollar worth now? So we have a situation where we have 8% annual interest rate, which is what we had in this table right here, 8% interest rate compounded annually for 4 years. Well, then the number of periods is going to be 4 because we are compounding once a year times 4 years, so it'll be 4. And then the 8% is going to be our annual interest rate. And so when we compare the 4 periods with the 8%, we know that today that dollar is worth 73.50 is worth 73.5 cents. But if it was anything other than a dollar, you would be saying that you would need 73.5% of whatever total you're aiming for today. If you're getting 8% quarterly or compounded quarterly for 3 years or 4 years, then you would get that. Or I mean, excuse me, annually for 4 years, that's what you would need. If you were compounding quarterly, then you would need 83.64 cents. Whoops, excuse me, 78.85 cents. Sorry, I missed. You would need 78.85 cents in that example. So again, you just got to go find the table that and multiply your principal value times that to give you the answer that you're looking for. But again, you can also calculate it using this formula where the future value, which is the value that you're aiming for, so that dollar value. So if you're looking for $1 4 years from now, is equal to the present value times 1 plus I, which is your interest rate, times the number of periods. So if you were trying to find $1, the value of $1 today, and you had an interest rate of 0.08 and it's compounded annually 4 times, well, then you would do 1.08 to the 4th power. So if you do 1.08 to the 4th power, you end up with 1.36. And then you would take that and divide it from the initial future value. So you do 1 over 1.36. And you get an answer of 0.7350. And if we go back to our table, we got 0.7350. So again, I could give you a tableless calculation for present value, and all you got to do is use this formula. So the table's great and all, but you're not constrained to problems with whole numbers and whole periods. You could do daily, you could do monthly, you could do annually, you could do semi-annually, you could do 1.19% as your rate with these formulas with future value and the compounded interest here. So even though I think your book might not address those, I feel like it's useful to address it now, even if it addresses it later with depreciation. So if you're comparing your compounded interest with present value, the one thing about this is that they're going to give you the same response. So if you're using present, if you have $80 now and you get 8% per year for 4 years, that means that you're going to get $108.84 4 years from now. If you want to know how much money you need to get to $108.84 4 years from now, if you're getting 8% per year, well, that table and the calculation that I showed you gives you a value of 0.735. So if you take 0.735 times 108.84, it tells you how much that is worth today and how much you need today to get there. So even though these numbers are different, they're moving in different directions, they're still yielding the same initial value and the same final value in terms of nominal dollars. So any questions? So here's another example. So if Renee wants $20,000 for college 4 years from now, and she can earn 8% compounded quarterly, well, then how much will she have to deposit in the bank right now? So 4 years from now, she'll have that 20 grand. So again, the first step is to calculate the number of periods, 4 years quarterly, 4 times 4 is 16. If it's 8%, then divided by 4, the rate is 2%. So if we go to the table, I guess cut off, but if you had the table, you could do 16 and 2%, and it would give you this value of 0.7284. In fact, we could actually use the formula to confirm this. So if you go to this formula, we want 20K. And we want to know what the present value is. We know it's going to be 1.02 to the 16. So if we do 1.02 to the 16th power, we get 1.3727. So if we do 1 divided by that 1.3727, this is 1.3727. So if we do 1 over that, we end up getting 0.7284. And if we go back to here, we get 0.7284. So the formula helps us find it, even though we didn't have the table. So if we multiply that times the 20,000 that Renee wants 4 years from now, that means they have to deposit $14,586 in the bank today, and then they'll have that 20 grand when they start college in 4 years, which is still 14. So any questions? So we have a couple they're going to pay them back at 8 years with 6% interest compounded semi-annually. How much will Lynn receive at the end of the 8 years? Well, if you're being compounded semi-annually, that means it's twice a year. So the number of periods is going to be 8 years times 2, which is 16 periods. Each period is going to be 6% divided by 2, which gives you 3% each time. And then from the table, you can calculate, okay, 16 periods, 3%, you get this multiplier, but we can also calculate that from our equation. So if I erase the ink on this slide, we had an interest rate of 0.06. It was twice a year, and then it was 8 years, so 2 times 8. So we get 1 plus, let's see here, 0.03, because we're doing 0.06 divided by 2 to the 16th power. So if you do 1.03 to the 16th power in your calculator, this is equal to 1.6047. If we go back to the example, we get 1.6047, and that's the same multiplier. So our formula is correct. So we do 40,000 times 1.6047, and we end up with a value of $64,188 as our total amount that Lynn will be repaid at the end of 8 years. So a lot of interest calculated over that 8 years with that interest rate, especially when it's compounded every 6 months. So any questions about how I calculated that problem? I think we have 1 or 2 more problems, and then that'll be everything. So hopefully this isn't necessarily the easiest thing. I think with the formula can look intimidating, but I think it's actually easier than the table. You just got to remember, because then you don't have to think about, oh, I need to divide this by n, because n is already built into the equation. But if the table works for you, that's perfectly fine as well. You just need to understand where that number is being generated from, and it's coming from that formula. So problem 1215, I don't know why there's a giant check mark. But anyways, Melvin is trying to decide whether to put their money in savings at Mystic Bank or Four Rivers Bank. I guess the check mark is saying that Mystic Bank should be where they put their money. But anyways, Mystic is offering 10% compounded twice a year. Four Rivers is offering 8% compounded 4 times a year, and Melvin has $10,000 to invest, and he's going to withdraw after 4 years. So that means n is going to be equal to 4 times 2 for Mystic, and it's going to be 4 times 4 for Four Rivers. So you get 16 periods for Four Rivers, 8 periods for Mystic. 10% divided by 2 means that your rate is 5. 8% divided by 4 means your rate is 2. If you go to the table, the multiplier will be 1.4775 for Mystic and 1.3728 for Four Rivers. So it turns out that this is your better option, because you're going to generate 47.75 in interest versus the 37.28. So even though Four Rivers is compounding more frequently and the effective rate may be marginally higher than for Mystic in terms of the relative to the initial rate, that initial rate of 10% is still going to provide a much higher return . 1.4775 is this. Connected for a second, so I apologize for that. I'm not sure how much you missed on the last problem, but I'm going to share my screen again. So for this previous problem, we had 8 periods versus 16 periods, because this was compounded quarterly instead of semi-annually, but the interest is still better for Mystic because that initial rate is higher, significantly higher. This is just essentially 10% divided by 2, which is 5, 1.05 to the 8th. And then this is essentially just 1.025 to the 16th, which is what's generating these values, because you're just using that equation that I gave you earlier. So any questions about this? Okay, we got a couple more problems here. So Lee Holmes deposits 15,000 in a new savings account, and then at the beginning of year 4, they deposit an additional 40,000. So what is the balance in Lee's account at the end? So the first step is you have to calculate the total principal amount in Lee's account after year 3. Whoops. So what you would do is you would determine, okay, well, if it's semi-annually, then that's 6 periods because it's 3 years times 2. The rate is 6% divided by 2, which is 3%. So the effective multiplier is, again, it's going to be 1.03 to the 6th power, which is this. Multiply that times 15,000. That means that his principal amount before he added the 40,000 was 17,911.50. Add the 40,000 in year 4, and this is his starting amount. And then you're going to have the same calculation for the multiplier, 1.03 to the 6th, and you end up with a final value of 69,152.12 at the end. That's how much money that Lee will have. So the trick in this problem was splitting off the interest into 2 periods, where, because you don't want to give 40,000 for the entire, but you're also compounding off of a larger number than the 40,000 because it's combined with the initial 17,911.50. So that's how you calculate that. And then lastly, Paul promises his grandson that he would give him $6,000 8 years from today for graduating high school. And so assume the money is worth 6% interest compounded semi-annually. So that's twice a year, 6%. So if this is 8 years, the number of periods is going to be 8 times 2, which is 16. The rate is going to be 6 divided by 2, which is 3%. So if we want to find the present value, we could go to a table and find this value, or we could use that equation. So 1.03 to the 16th is going to give you 1.6047. So you would do 1 over 1.6047. And you get confirm that is the correct multiplier. And so this means that if Jamie's grandfather, have the $6,000 to give to his grandson without actually having to accumulate more income. So again, this was probably found from the table, but if you use that present value formula, you know that the rate is 0.03, you know the periods is 16, and then you would take 1 divided by this answer because we're discounting it, and that would give you the actual answer for this multiplier times the value that you want at the end, and that gives you the beginning value that you need to start with. So, does anybody have any questions?